Thank you, Dr. Pham. We will hear next from Dr. Vasily Krivitsov. Vasily is employed by Ford Motor Company as a senior staff technical specialist, and he's special to us because he's a graduate of the reliability program here at the University of Maryland. He's published many papers, co-author of one very good textbook that is used in the curriculum here. Vasily.
Thank you, Dr. Roche. So as we all know, the reliability engineering program at this university offers really good fundamentals for future engineers to practice reliability discipline, in the field. And like I said, the fundamentals are primarily oriented to give students basic knowledge in probabilistic models, statistical estimation, system engineering elements, etc., etc. So in this quick talk, I would like to offer one reliability education opportunity that could be offered as a course in reliability engineering, because once again, all the bits and pieces are available through the program. But after 15-year experience in the field, I realized that there might be a separate course which would be addressing some specific issues with which reliability engineers have to deal in practice. So, here's a quick discussion outline where we'll go through the practical importance. And by the way, and this specific course, I forgot to mention, is actually reliability analysis of field data. So, very specific area of reliability which deserves an explicit course, in my opinion. So, practical importance of reliability analysis of field data, I'll talk briefly on that one. Then the rest of the presentation, the bulk of the presentation will be devoted to some modeling peculiarities which are related specifically to the field data analysis. I will show you, and this will be illustrated by, case studies, actual practical case studies from corporate experience. And then, in the end, I even would like to propose a potential course structure which could be designed to cover this material. So, practical importance of reliability analysis of field data. Why is field data so important to be analyzed properly for the future product development and production of reliable systems and components? First of all, the first aspect is the root cause analysis and future failure avoidance through statistical engineering inferences on the failure trends and factors affecting them, right? So, needless to say that all our reliability efforts, ranging from reliability-oriented design. In fact, there is a school of thought which is called design for reliability, including all the sophisticated testing, reliability testing that we do before releasing the product in the field. All those then all those are ultimately verified in the field, because field environment is the ultimate measure of how a given design performs. So therefore, by collecting the field data and analyze them correctly, number one, we can establish the root cause of failures that helps to understand the physics of failures, just by carefully looking at statistical trends that failure rate exhibits in the field. And second of all, that knowledge could be, of course, used in terms of future failure avoidance in order to prevent failures in the future. Next one is the lab test correlation. In many industries, they use the notion of the so-called key life test, where in an accelerated fashion, all the major stress factors from the field are introduced into the lab environment. The question becomes, how realistic are those factors introduced in the lab environment? How realistically do they represent actual field usage? And therefore, collecting the field data on one hand and having the lab data on the other hand. For example, you can use a non-statistical technique called QQ regression, quantile regression, helps you to calibrate lab testing to the actual ultimate field environment. Next one is cost avoidance through early detection of field reliability concerns. Once again, we can devise sensitive statistical procedures which would be looking at the failure rate developing in the field, and of course the big challenge there is to becomes to distinguish the noise from the signal. In fact, today as we speak, there is a hearing on Capitol Hill, if some of you may know or may pay attention, right? On the GM ignition switch problem, right? Which actually developed about 10 years ago, and this is exactly relative to the third bullet point, where it's not only cost avoidance, it's also risk in a bigger sense, also human life type implications. And so the problem for GM, from this brief analysis of what I've heard yesterday and parts, in parts through the paper today, is that they apparently did not have good enough early detection procedure for them to distinguish the signal from the noise. And therefore, the signal did exist, and in fact, NHTSA acknowledges that, National Highway Traffic Safety Administration. But both NHTSA and GM didn't have enough resolution to be able to say, yes, that's a definite signal, that's a definite problem, we should take care of it right away, right? And then finally, the final practical importance of field data analysis is cash flow optimization through the prediction of required warranty reserve and the expected maintenance costs, right? Once again, the scheme is very clear. Once I collect the field data, I can construct a probability distribution representing the failure probability in the field. I can extrapolate it through the end of the warranty period, and therefore I could predict the required warranty reserve. And that is a very important aspect of reliability modeling. So, and in the subsequent slides, like I said, I'd like to cover a few practical scenarios which is peculiar to the field data analysis. So first of all, relates to the staggered production and sales. I guess this numerical example would be easier to understand. So basically, in any commercial producer or manufacturer who's in a mass production business has a phenomena of devising a design, and that design gets introduced in the field. But the thing is that if your plant volume for the field is 1 million units, of course you understand that not all 1 million units gets produced and released to the field on the same day. If this was the case, that would be easy for reliability modeling, right? Because you know that your population would be homogeneously accumulating usage in the field, and therefore any failures that are coming from the field could be easily normalized. But realistically, we have to deal with staggered production, and I'm not sure if, how to engage the laser pointer? The middle button? Oh. Right. Oh well. Anyways, there is a staggered production, and then since the population gets introduced into the field by subpopulations, therefore the respective failures are also coming as subpopulations. And therefore, you have to apply, in fact, the procedure is known, called Kaplan-Meier survival analysis procedure, estimation procedure. But the thing is that this format is very typical for the field data. So every manufacturer, like I said before, who is mass production business, would deal, in fact, one of the software products called ReliSoft Viable++, they call it Nevada chart, just because this chart reminds geometrically reminds the contour of the state of Nevada, right? Which is triangular. So the point is that if we can teach that ahead of time within a specific course, this could be this knowledge could be carried away for a reliability professional and ready to be used in the field. So therefore, this slide was to illustrate this typical data format. This slide just formalizes this in terms of in general terms, and then there is some peculiarities. For example, again, for any industry that offers a two-dimensional warranty plan bounded by time and usage, of course, in automotive industry, the usage is the mileage, right? So therefore, you see that the x-axis on this chart is the time and service, the y-axis is the mileage, and then you have to also, once you are modeling and estimating the data from the field, you have to account for the phenomena that for any time conditional distribution of mileages, there will be a tail which is expiring from mileage before expiring from time. And again, if I had a pointer, but I think you can visualize that, right? So, oh, thank you, sir. This helps a lot. Okay, so for this subpopulation, this population is still 2 years old, so it is it's within the time-bound warranty, because the limit for the warranty is 36 months of service in this case, right? But this subpopulation would be out of warranty just because they accumulated mileage faster and they expire by warranty, right? So once again, this is a very common phenomenon, not only in automotive industry, but in any industry which is offering two-dimensional plans. And this could be taught how to deal with the situations, okay? And then, of course, the practical importance of this, once you correctly estimate the non-parametric form of the probability of failure in the field, then you can easily put it on a viable probability paper, right? And the actual practical financial implication for the company would be, this would be the predicted failure probability at the point in time of interest, okay? If you know the population size, you can calculate the total expected number of failures, multiply it by the cost per repair, and therefore you would arrive to the required warranty reserve, right? So once again, this is a very typical situation in the field, and this could be taught ahead of time. Now, very often, so let's say I predict this amount of warranty reserve for a given component based on its reliability in the field. Next question becomes, this would be the ultimate reserve, right? Question is, how is this amount of money or these amount of failures will be distributed in calendar time? Because you see, this axis is not calendar time. It's the time, or it's the age of the component, right? So therefore, you do another more or less straightforward calculation, and again, it becomes straightforward once you derive it, right? So you basically then recalculate. You take, you would take this number of failures here, 15,000, which is the ultimate number of failures to be warranty returns to be expected, right? And then you take those 15,000, and with a special calculation, you break it down by months. So in October, you will have 600 of those. In November, you have another 2,200, etc., etc. And this is very helpful, first of all, for logistics purposes. How many spare parts to plan and provide to the dealer for the replacement, and second of all, for the financial purposes. And once again, this is a typical situation which could be formalized and taught how to deal, for the students to deal with. So now, non-homogeneous production quality. Another very typical situation. So on the x-axis, I'm plotting, this is, by the way, this is one and the same nominally identical design. But due to whatever reasons, such as supplier issues, material variability properties, you have a very non-homogeneous quality in the field, or reliability in the field. So the x-axis on this chart is different production months, over several model years. And the y-axis is actually a scaled probability of failure. The reason I say scaled, don't be confused by the number. 70, for example, 70 means not 70% of failure, it's 70 per 1,000 vehicles, right? So therefore it's a scaled probability of failure. But the point is in this chart that, as you can see, the reliability for the nominally identical population is varying greatly. Question is, how do you handle that statistically if you have to still produce the result? And the answer that comes in place, and by the way, I borrowed this model from the biostats, and of course, Dr. Maderos was teaching a model similar to this called accelerated life model, where you can introduce a covariate. In addition to just modeling the probability of failure as a function of time, you introduce a covariate, such as a stress, but in this case, my covariate would be the production months. So I'm actually treating each individual production months as a covariate in this model, and therefore, ultimately, I'm arriving to the prediction where, using that model, where I'm modeling each production months explicitly through one common model, okay? And then, of course, I do the correction for the two-dimensional warranty reduction, and this would be the ultimately estimated probability of failure in the field at 60 months of service, which is 5 years, right? Once again, these probabilities are then can then get converted into the cost, and their special reserve could be allocated. Okay, next example, time versus usage. You know, again, I'm using the automotive industry example. You know, you have a failure in the field. The failure happens at 3 years and 15,000 miles. For the second unit, the failure happens at 2 years and 70,000 miles, etc., etc. Question is, how do you model the probability of failure? Do you model it as a function of time in service, or do you model as a function of mileage? In some instances, the discrimination is relatively simple, because if this is what we call a time-driven failure mode, such as corrosion, we know that the corrosion would be better represented by, if you model as a function of time, because it happens irrespective of whether or not you are driving the vehicle. However, if you model the ball bearing fatigue, then of course mileage would be a better indicator. Again, a range of models exist in this respect, and Dr. Roche, as you can see, I'm accelerating my slides because, like, Dr. Roche indicated they have a lot of material, there's no way I will cover it. And I said I will, so I have to see. So, there are a few existing models which are published, like the one from Hu, Lawless, and Suzuki here. There's another one by Kordonski and Gersbach, which again could be taught, and people could be trained in how to distinguish the situations. But of course, the ultimate solution, if you're in doubt, and again, we practice this at Ford, we constructed this our model ourselves, is what we call a bivariate probability model, right? Where on one of the axes, I'm modeling my time and service, my time element, and on the other axis, I'm modeling my mileage element, right? And therefore, conveniently, now I don't have to debate any longer, right? I can conveniently extrapolate simultaneously time and mileage, and again, this model could be taught as a fundamental to deal with the field data analysis issues for a reliability engineer. So, next one, and by the way, this slide I'm showing to you just to show how important it is, that it actually matters and it is used. You know, I heard from one of the in one of the conversations here during the break, that in some cases the reliability engineering is still looked at as a supplementary activity for any mainstream engineering, such as mechanical engineering, materials engineering design. I'd like to propose that it's no longer supplementary, it's actually mainstream, because if you look at the implications, like for example this case study, please don't take any numbers from the slide, just to give you a feeling, right? That so from the two-dimensional model, we are predicting the probability of failures for each of these population of cars. You have Super Duty, you have F-150, here's the population affected in the field, and as you can see, the probability of failure is actually relatively very low, right? But given the population in the field, and given the cost implications, this is what you're looking in terms of cost implications to a given supplier, right? So once again, this is a classical example in automotive industry, what we would call probabilistic risk assessment, because risk, as you know, there's always two components. There's a probabilistic components and there's implications components, right? So this is your you know, real world data and real world implications. Okay? So now, another phenomena which is typical for field data analysis is the so-called field service bulletins. So what happens is that as you look at the field data and you observe some failures, there is some external non-random events which influence some spikes in the field. For example, as manufacturer discovers a problem and they have a corrective action, they inform dealers, they publish a so-called field service bulletin, right? Which is an instruction for a dealer to pay attention to a particular failure mode. So if a person comes for an oil change, of course this doesn't concern safety, because safety failure modes which are related to vehicle safety, they are handled quite differently. But milder, such as cup holders or some kind of radio, some customer satisfaction issues, we published field service bulletins. And the question is, once that bulletin is in the field, it introduces a random bias to my probability of failure, because out of a sudden, dealers start repairing a given component with a much higher frequency. So question is, how do we address this mathematically, and how can we predict impact of the published bulletin, and how can we distinguish the actual failure rate from the one introduced by this bulletin, right? Again, there is a convenient model, also in the class of the survival regression models, the so-called time-dependent covariate, where I can introduce this additional factor as a time-dependent covariate into the model. And after modeling, I could easily then distinguish the expected, in this case, I'm plotting the conditional probability of failure, also known as a hazard rate, right? But as you can see, the taller bars would be the impact of the TSB, Technical Service Bulletin, and the smaller bar would be the actual underlying failure rate. Again, helps us to distinguish, to decouple the influence of this Technical Service Bulletin. There is another whole issue related to the field data called seasonality. You know, many failure modes are affected by temperature, right? And we can model, there are several models which are available to model seasonality, one of which you see on the screen. Another one would be to just break down to stratify the failure probability by climate. For example, you can treat the southern states as one subpopulation, although it's a nominally identical population of cars, but have different usage and different, you know, external factors that influencing. So you can do the southern states with the northern states, which provides more accurate inferences. Okay. Now, data maturity. This is probably one of the most notorious problem, and let me explain it just for one particular example. So what happens here? I'm looking at the probability of failure. In this case, my y-axis is the CDF, cumulative distribution function, as a function of time. So forget the two-dimensional aspect, which is another factor, but in this case, let's look at simplistically as a function of time. And first time in this data set, I look at this data in January 2006. And you see, and that corresponds to this low curve here, right? Now, when I keep observing that population in the field, you know, it's not strong of a signal for me, it's not a reason for a recall or anything. I'd like to watch it how it develops in the field. However, when I analyze data in March of 2006, you would think there would be additional volume sold in the field and there would be additional failures accumulated. But if I do Kaplan-Meier procedure, I should normalize them nicely, and therefore the second observation curve should be coinciding with the first one, just a longer curve, because I have more data to observe, right? However, what happens, that entire curve, that entire CDF tends to move up. Why? I have a nominally identical homogeneous population of products. Why, if I evaluate at different observation times, why does my CDF estimate change? Right? And then, of course, if I observe it in May 06, you see this curve is totally different from the first one. And one of the factors that we uncoupled in this case is the so-called lot rot problem. You see, even though the population is homogeneously identical, but not all the units get sold simultaneously. And therefore, some of the units are sitting on the dealer's lot or in some kind of warehouse, if this is not automotive industry, right? And while sitting in the warehouse, again, remember from Dr. Maderos' teaching, they subject the so-called dormant failure rates, right? In terms of the car, I give you a simple example. The tires develop the so-called flat spot, right? So if they're sitting without being sold, in fact, you would think ball bearings, okay, tires are obvious, batteries are obvious. Why would ball bearings reliability depend how much time a car spends on the dealer's lot before getting sold? The answer is because there is internal lubrication inside the ball bearing. And when sitting for a long time, it tends to gravitate to a lower point. And therefore, upper part of ball bearing, on the microscopic level, gets exposed without lubrication, you know, due to some kind of heat or whatever it experiences, right? In other words, cars would like to be driven. If you buy a car, you better drive it. Don't let it sit, whether on the dealer's lot or in your garage, right? They like to be driven because many factors are dependent on them. So anyways, what I'm trying to say, now that you understand this phenomena, you can now, what I did in this case, I introduced the number of days they spend on the lot as a covariate in the accelerated life model. To me, it's almost like acceleration factor, right? Once I decouple it and, uncompensate for that factor, here's my lower graph. You see, here's my first observation, second is an extension, third is an extension. In other words, there is no there is no more dissonance between these curves like it was in this case, right? This is what we refer to data maturity. And there are some different reasons for data maturity. Another one is so-called the reporting delays. Another one is so-called warranty expiration rush. And again, in the interest of time, I'll mention them quickly. So, to summarize, here is a proposed course structure that could be developed just to address this specific discipline, reliability analysis of field data. Of course, you know, the first big bullet is basically course motivation. You know, could be covered, why it is practically important to cover this discipline. In the second bullet, it would be nice to review all basic probabilistic models and respective estimation procedures related to this case, such as lifetime probability distributions, which is already covered in Dr. Mosley's, Dr. Maderas' courses, right? Next one is reliability with exploratory variables. Again, accelerated life testing model is one such model. Proportional Cox model, survival regression, a couple of other models which could be covered and which becomes useful. Next one, and next one is a combination of reliability models such as distribution mixture and competing risk models. Again, a quick overview, and that will set a good fundamental basis. And then for the repairable system analysis, of course, we have an entire different set of models such as ordinary renewal process, non-homogeneous Poisson process, generalized renewal process. And then once we cover these fundamentals here, now we can start talking about those practical modeling scenarios, the one that I covered, right? Staggered production, non-homogeneous production quality, seasonality, etc., etc. And we show how those specific models could be used to cover those scenarios. And I even picked up a couple of books, of course, one for obvious reasons because I co-authored with Dr. Maderas, and the other one which I find quite